Hey, physics studies, how's it going? So in this series of videos, we're going to be talking about radiation, all the different types of radiation, accompanying particles, and then we'll probably be calculating the energy released in some of these radiation using our mass defect that we had in the previous, I'm just looking down here, the previous lesson? Yeah, in the previous lesson. Okay. So radiation was discovered by Becquerel again by accident, right? I talked about that already, where he put a chunk of radioactive ore in his desk, and he noticed that his photoplate was exposed. So he noticed that the EMR was interacting with that. I'm going to change this filter. It's a little bit crazy. Okay, let's change it to something less crazy. Maybe these goggles again. Yeah, let's do this one for now. Okay. So the three types of radiation that were discovered by Madame Curie and Pierre Curie when they were doing their experimentation was alpha decay. Okay, alpha rays, sorry, is just a beam of helium nuclei. So not an atom. So these are charged particles. They've lost their electrons. So we call that, well, we don't call it that, but you can see on the periodic table, if I pull out my periodic table, if I can find one, I seem to have lost all my mind as well here. So let me see if I can find, oh, no. How is it possible? Just 1 second. All right. So up at the top, not that top, on this top over here, you can see helium. Helium's atomic number is 2. Its atomic mass is 4. So it has 2 protons and 2 neutrons, most likely. In this case, it's a helium-4 nucleus, very specific type of nucleus here. So its symbol later on it could be written as a few different ways. You could just write it as an alpha particle, or you can write it as helium-4, right? Or sometimes you can write out the numbers that go with the alpha particle too. So you can write out either one of those. So it's just a charged particle. It's a charge of positive 2. You'll find that on your constant sheet as well. So alpha particle. They even give you the mass as well in the formula sheet here. So that's my alpha particle charge plus 2. Okay. They realized there's other beams as well. There's one called a beta ray. A beta ray comes in 2 different types. This one's a beta. This one's very specific to talk about electrons. This is beta negative. Right? Beta negative. There is a thing where you can have beta positive as well. And beta positive doesn't involve electrons, it involves positrons. And a positron is an anti-electron. It's an antimatter version of an electron. So a beta negative or beta positive. Okay. And we'll talk about the 2 types and where they come from. Like beta positive is very common in bananas. And beta negative is more common in other types of radiation. You'll see. Okay. It's an electron. We'll deal with that when we write it later on, what it'll look like. Gamma radiation is just photons, just gamma rays. It's part of the EMR spectrum. It's really, really short wavelengths, high frequencies, high energy. So it even says your high energy photons. And those are denoted by the symbol gamma. It's like an upside down kind of, I don't know, ribbon kind of thing going on there. Okay. Now all the particles there, they just determine that they have different charges based on the curvature, the different masses, assuming that they all have the same speed, based on also the curvature. And you can see that here, gamma doesn't have a curvature because it doesn't have a charge. If it doesn't have a charge, it's not going to be affected by a magnetic field, because a moving charge produces a magnetic field. Those 2 fields, the external one that's shown in the picture here, will interact. Based on the hand rules, you can determine which way they turn. Okay? So based on this, I could just see, using my hand rule, out of the page, particles going that way. The beta is a negative charge in this one, so this is beta negative. Right? Now, if it was going the other way, we would have beta positive. Right? So this is beta negative. This one over here is obviously a positive charge. And this one here is no charge. That's very key for some of the stuff that we're going to be doing, because we're going to be talking about conservation of charge, conservation of nucleons, not necessarily conservation of mass. It's already been proven from the previous lesson that you can lose mass. When you lose mass, you gain energy, or you lose energy to the surroundings. Okay. So an alpha particle, just an emission of a particle made up of 2 protons, 2 neutrons. You can see down here in the nuclear notation, the bottom number, remember, that's your proton number. The top number is your nucleon number. So that's 2 protons and 2 neutrons because they add up to 4. Here I'm missing what particle this actually is. Maybe I should put that in there. So it's basically just a helium atom stripped of its electrons. It's positively charged. I don't have to put the positive part there. You can just see that from the bottom, because the bottom now can represent our charge, because the bottom is the number of protons usually. When you talk about this in terms of electrons, you're going to see that you put a negative there. What doesn't mean you have negative protons, that just means you have a negative charge. Okay. This here, I'm just going to erase this. I'm going to put that over here. 88,223. I just have to put that chemical there. I keep on forgetting to do it every year. But 88 is radium. Okay. Now, one thing that's missing here is that this radium, actually, I won't say I'm missing it. I'm just going to put this little asterisk beside it. This just indicates that this is an excited atom. When atoms undergo radiation like this, when they lose a piece of themselves, they become excited. Their electrons are in the wrong spot, because the electrons are supposed to be in the shell based on a 90 proton atom. So they have a different electron configuration. And as soon as you lose 2 protons, your shells have to change to accommodate that. So now your shells are based on a 88 proton atom. But that change, but before it changes, it's excited, but it's going to have to change to this new energy shell configuration. And when it does that, it de-excites, all the electrons move around, and it emits gamma radiation. So this little excited, this is like an intermediate step here. So after this, when it becomes unexcited, I could say that the alpha particle got emitted there. This is no longer going to be excited. Its energy level configuration is changed, and it emits a gamma particle to go with it, gamma ray. Okay, so that's very key. That for alpha rate decay, gamma decay is always going to come out as well, right? They are hand in hand. So this intermediate step here, we usually don't draw this intermediate step where this excited element is, but it is there. Okay, so what do we notice about the nucleons and the protons in this reaction? Okay, so if you look at the top, or let's look at the bottom numbers, the proton numbers. So I start off with 90 protons, and I have 2 in the alpha particle and 2 in the radon. Or sorry, not 2, 88 in the radon. But if I add the 88 and the 2 together, I get 90. Okay, so I'm going to cross out the word matter and actually change that to a little bit later on. Now, the protons are being conserved, which also means the charge is being conserved. I had 90 positive pieces before. I have 90 positive pieces afterwards. They are the same. What do we notice about the nucleons on the top numbers? So I had 227 to start off with. 4 plus 223. 4 plus 220. Now, a gamma particle, it's being released here, but a gamma particle is a massless particle. It's a photon. It's EMR. It doesn't have any mass at all. Travel at the speed of light. Photons always travel at the speed of light because they have no mass. That's very key. If you have no mass, you always travel at the speed of light. Now, it's based on the little picture above us. It has no charge, so the bottom number is 0, and the top number is 0, so that plays into this as well. So add all the numbers together on the top here, I get 227. So start off with 227, end up with 227. Now, okay, I'll put the word matter back there. This is not mass. Mass and matter are slightly different. Matter is like the pieces. Mass is how much it actually has in it, like the weight of it. These are based on the nucleons. Now, those nucleons are being conserved, right? So nucleons. Okay. So conservation matter, conservation charge, these things, but not mass. Mass changes. Usually in these kind of cases, the mass on the left-hand side, the reactants, is larger than the mass of the products. So I've lost mass, energy comes out. And most of the time it's energy of kinetic energy. The photon energy is a little bit different because that's from the moving charges and stuff. But there'll be kinetic energy. These guys will be moving away from each other pretty fast. So there is energy in those two particles there. Okay. Yeah, we were talking about this. Alpha radiation can be written as this way. It could be written the same way. Alpha particle there, right? So those are the same thing. They're interchangeable between each other. So if you ever see a helium nucleus like this, it's the same as an alpha particle. It's not a helium atom. Now, there are some things like this uranium, that is an atom. So it does have 92 electrons because an atom has, so this here, just I'll put up here, not an atom, right? So not an atom, right? So no electrons. But most of the time we talk about bigger particles like this uranium, it is an atom. So an atom is neutral to start off with. So if it has 92 protons, it has 92 electrons. That is kind of key for some math later on, okay? Now, whatever particle it creates here, when it undergoes alpha decay, is most likely going to be excited. Now, remember, like we said, I don't draw in that excited state, so I'll just assume that it goes to be non-excited, so it's going to release a gamma particle as well. Okay, so what does it produce? Well, the bottom numbers have to add up to 92 because I start off with 92. If there's anything else on this side, you have to add those all together, but right now there's only one thing, just the uranium. So this is going to create 90, okay? And you look at your periodic table. I got a bunch of math on the bottom back of mine. 90, right down here. Thorium. So it's going to produce thorium. And the top numbers have had to add up as well. So I had to add up to 234. I've used 4 up already, so this has got to be 230 plus that. And there we go. That's pretty cool. That's crazy. Thorium 230. Most likely it's supposed to be 232. Pretty much everything after radium, or even radon, is radioactive. So this is, no matter what kind of isotope it is, most likely radioactive. A few things about this is that there is a name to most of these particles, like the particle that you start off with, like you can see on the next page here. That is the parent particle. And the larger particles, usually not the other guys here, right? Not helium. Helium I wouldn't consider a daughter particle. I just call that radiation. But usually it's the larger ones are called daughter particles. So sometimes it could break up into 2 bigger pieces, and those 2 bigger pieces would be daughters, so to have multiple daughters. Okay? That's just that definition page there. Now, first of all, let's look at these and say, are these possible? Let's ignore the fact that they don't have the gamma in them, but do they actually work? Right? So that could be a typical question, is does this actually work? So it's polonium turns to lead. So first of all, I want to know is polonium 84? Yep. Lead is 82? Yep. Okay, that's good. Do the bottom numbers add up? 82 plus 2? Yep, the bottom numbers add up. That's good. Protons work. Now the top numbers, let's add those top numbers up there. So 208 for, that ends up being 212, doesn't it? So that does not work. Okay, so this one does not work. There's a little sad face there. Let's look at the next one here. 88 plus 2, add up to 90. Okay, so that works out nicely for us. The top number, 226 plus 4 is 230. So that one works. Cool. And the bottom one, okay, so if you ever see this neutron, you notice that a neutron, the bottom number is 0. Remember, the bottom number represents proton count. A neutron is not a proton, so it makes sense the bottom number is 0. The top number is the nucleon count. There's only 1. So you have no protons, but you have 1 nucleon, so that must be a neutron. Right? So this is 1, 0 just represents a neutron. Okay? Let's see, what if they add up? Does it actually work? If you notice on the bottom on this side, 28 and 0, that adds up to 28. But that doesn't work because I started off at 27. And the top doesn't work as well because it adds up to 61, but I started off at 60. So that doesn't work as well. So this sad face for that last one there. Okay, let's keep on going. Okay, so I'm going to stop the video here. I want you to try this question out. We'll go to part 2 in a bit. I'll see you then.